Hi students, welcome to the video lectures of speech and natural language processing. Today let us discuss about the tokenization. What is tokenization? Tokenization is the process of splitting text into smaller units, usually words or subwords, for easier processing and analysis by NLP systems. So each unit or token represents a word, part of a word, or even a punctuation mark, depending on the tokenization strategy. So what is the importance of tokenization in NLP? So basically it is used in text pre-processing, transforming raw text into a form that can be analyzed computationally, and also helps in preparing data for downstream NLP tasks like sentiment analysis, machine translation, and text classification. Then, what are types of tokenization? So first type is word tokenization. So the word tokenization will split the text at word level, separating words and punctuation marks. For example, if you give a word like "I love NLP," so what it does is it just divides or splits this into the tokens. So you have said "I love NLP" as an input. If you give, you'll get "I" as a separate token, "love" as a separate token, and "NLP" as a separate token. This is what about your word tokenizations. And second one is sentence tokenization. So when I say sentence tokenization, so it divides the text into sentences. Okay. So suppose if you give an input as tokenization is important, it helps pre-processes text. And the output what you get is tokenization is important. This is considered as a first sentence tokenization. Second sentence is it helps pre-processes the text. This is second sentence. So single sentence or single input what you gave have been divided into two sentences. That is what is your sentence tokenization is. And then is subword tokenization. We also call as byte pair encoding BPE. This will split words into smaller subword units, especially useful for languages with large vocabularies or morphologically complex languages. So basically, this is commonly used in your neural machine translations and transformer-based models. Transformer-based models are nothing but your GPTs and as well as the BERTs, BERT. An example what you can consider is a word like simply unhappiness. So it will what it will do is so it will have a subword tokenization, that is it divides your unhappiness into un as an one token, happy as one token, and NES as another token. This is what happens typically with your subword tokenization. Then we talk about character tokenization, which breaks text into individual characters, often used in character level language models. So if you give an input as NLP, so what it does is it divides each character as a tokens. So N is one output or one token, L is another token, and P is another token. So that is how character tokenization works. So then we talk about the challenges what we have in tokenization. So first one is ambiguity. So when I say ambiguity, in this tokenization particularly, the ambiguity refers to the languages where we don't really find the boundaries of the words to tokenize or to split into some words. The languages like Chinese or Japanese or Thai, where they don't use spaces between the words, that is where your ambiguity exists. Second is the handling punctuation marks. Yes, and the punctuation marks need to be handled very careful because it have some important information in it. Either it might be a syntactic or semantic, even something commas or full stop, everything matters. So then we talk about multi-word expressions. So multi-word expressions are nothing but when you try to give a word which have a meaning when it is treated as single. That means if I say machine learning, so while we write machine learning, we don't write machine learning as a continuous word. Rather, what we do is we give a space between machine and learning, right? So if it treats the machine as one token and learning as another token, then the total meaning changes. That means the context or what you're trying to incorporate that word in a sentence, it will lose its entire meaning. So there should be a mechanism to treat these as valid multi-word expression. That means if you say New York, so while we write it, we generally say new space YORK, New York. Or when we say machine learning, we say machine space learning. So this has to be treated into one. So yes, so the simple tokenizers, what they do is they just split this into two words. That is another challenge. Then we talk about language variability. So language variability is nothing but so where you find rich morphology in the languages. So rich morphology in the sense rich inflection that we have. In previous videos also we talked about few languages like Finnish or Turkish who have who are rich in morphology. These are rich morphology languages we call. So these present challenges for our word level tokenization because of their complex inflections. Then we talk about special characters and emojis. So dealing with these special characters like at the rate, hash, or any other emojis in informal text, we find them like social medias, generating a lot of data where we find these things in that. These can make tokenization more challenging actually. So then we talk about tokenization approaches. So first one is rule-based approach. So rule-based approach is you can see here uses predefined rules and regular expression to split the text. So when we say it uses these predefined rules or regular expressions to split the text, it seems to be simple and fast, but it struggles with ambiguities in complex languages. When we talk about statistical tokenization, which uses probabilistic models trained on large corpora to predict where tokens should be split. So statistical tokenization ensures accuracy, and it is also considered to be more flexible one than the other models and robust even than your earlier rule-based tokenizations, what we had discussed just now. But the only issue is it requires some huge data to be trained on, right? And we move on to the next one, that is subword tokenization, BPE or word piece. So especially useful for handling rare words and out of vocabulary terms by breaking them down into smaller recognizable subword units. So these are popular in your models like BERT or GPTs and transformer-based systems. Then tokenization and NLP applications, sorry. First one is text classification. So tokenization breaks down the text into units that can be fed into ML models for tasks like sentiment analysis, spam detection, or topic classification. So using the analysis, it will try to detect it. Okay. Then second is machine translation. Tokenization is critical in translation tasks, allowing models to handle vocabulary efficiently and process both frequent and rare words. Then is named entity recognition. So you all know about NER. We have discussed in our previous videos as well. So correct tokenization helps identify named entities in a sentence, which may consist of multiple words. Example is New York City. Then is the next application is search engines. So tokenization helps search engines process user queries and match them with relevant documents in their index. Then here is a sample code snippet where we try to implement the tokenization in our real time. So yes, hope you all are aware of your NLTK libraries, which stands for Natural Language Toolkit. So we are trying to, yeah, just a second. Yeah, here you can see we are importing our NLTK libraries. That is your Natural Language Toolkit, and we are importing word tokenize and sentence tokenize. Okay. So these two are the functions which will perform your tokenization of words and tokenization of sentences. These are the two varieties which we have seen in the earlier slides. So then I'm trying to download PUNKT. So this resource where this will this is a pre-trained model, okay, which will tokenize now the text into words and sentences. Okay. Then we are taking a sample text here. Hello world. This is an example of tokenization. Let's break down it into tokens. This is the sample text we are taking. Then this is for sentence tokenization, and this is for word tokenization. So both the functions we are declaring here, where the function will break the text into sentences here, and the results are printed out as sentences. Okay. Then here what happens is this function will break the text into words, and the result is printed as words. Clear? This is what is your implementation of tokenization. This is how the output looks like for the given input. You can see the text, whatever we have given, the sample text. Hello world, this is an example of tokenization. Let's break it down into sentences. And this is how your sentence tokens is giving the output. This is how your word token is giving the output. You can see the split up of the nature of the tokenization what we applied. So sentence tokenization, it is making the input into sentences here, you can see. And the word tokenization, for the given input, it is breaking down everything into words. This is the difference. Hope you got it. So next we move on to the next concept called stemming. Okay, so stemming is a crucial text normalization technique used in NLP to reduce words to their root or base form. The root form produced by stemming may not be necessarily be a valid word in the language, but the goal is to map different forms of the same word to a common base form. This process helps in reducing the complexity of linguistic data and is useful in many NLP applications like information retrieval, text classification, and search engines. So what did you understand by this stemming? It is just removing of your affixes, that is your prefix or suffix or infix from a word to reduce it to its base form or the root form or stem we say. So the purpose is to group words with the same base meaning together, reducing the complexity of text data by ignoring morphological variants of words. So stemming versus lemmatization. Okay. So in our previous slide, you have seen stemming is a process of removing the affixes, right? So for example, if I say a word called running, you can understand from this, like this will be stemmed to its root word. When I say running, it will remove that ing and it will break down it and brings down to the base word called run, run, run. And even for the same example, if you give runner as an input, it will break down and it stems down into run. This is how your stemming looks like. So there's a comparison now between stemming and lemmatization, where you can see the resultant word in stemming may or may not be a valid word, but the resultant word in lemmatization will be a valid word. For example, if I say a word called caring, caring, so this caring word, when you give it to stemming, it gives you the output as car, car, as it removes or stems down or chops off ing in caring. Whereas the lemmatization takes care of the vocabulary where it should have, it should be a valid one, like it should give a meaning. So what it does is it ensures the result is a valid word in the language. So how it is ensuring? When you give the same example caring to lemmatization, it gives the output as care, care. So then we talk about types of stemming what we have. So first one is Potter stemmer. This is one of the most popular and widely used stemming algorithms. So basically it removes the suffixes ings, eds, and s based on a set of rules. If I say flies, it will reduce it to fly. Okay, and it goes on. The examples, the input words, if you give playing, played, plays, player, The Potter stemmer outputs them as in this way. For playing, it will convert into play. For played, it will convert into play. For plays also, it's stemmed down to play. For player, it remains player. So these input words are common for the next coming other types of stemming algorithms. Okay. So next, the other types of stemming algorithms are snowball stemmer. So this is an improved version of the Potter stemmer, where it is designed to be more accurate and efficient than this earlier one. So basically, this has a nature of supporting multiple languages. Okay, so then next we talk, and the output you can see play, 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 player. This is the output for the input what we have given here. These are the input words, and these input words are common for all types of stemming. What I'm displaying in the next slides also. Next is Lancaster stemmer. So a more aggressive stemmer compared to Porter or Snowball, often reducing the words excessively. So if you say happily, it will reduce it to hap. If you say runner, it reduces to run. And if you say running, it reduces to run. So this is not as commonly used due to this aggressiveness only. Okay. And then is Lowen stemmer. So one of the earliest stemming algorithms, which uses a large set of rules for stripping suffixes. If I say connection, what it does is the Lowen stemmer convert into connect. If I say communities, it will say commune, COMMUN. That is how it behaves. And the output for the earlier inputs are play, 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 and play. Okay. You're seeing a change here. The player have been converted into play in Lancaster stemmer as well as Lowen stemmer. Now let us try to talk about the challenges that what we face in stemming. Okay, so the challenges here are overstemming, understemming, and ambiguity. Right. So basically, the overstemming is occurs when the stemming removes too much, resulting in stems that are unrelated to the original meaning of the word. Then is understemming. This happens when the stemmer fails to strip enough characters, resulting in words that should have been merged, still remaining distinct. And then ambiguity. Stemming can lead to ambiguity where different words are reduced to the same stem, even though their meanings are different. Okay. So that is about your ambiguity challenge in stemming. Okay. So example for your overstemming can be when I say university, it stems to universe. When I say organization, it stems to organ. So for the example for your understemming can be general and generally, where this remains as two different stems. Okay. And for ambiguity, you can say the universe and university, which might be reduced to the same stem called universe. So these are the challenges. So this is a sample code where you can see we are trying to incorporate or we are trying to implement, um, the stemming here. So here we are importing the natural language toolkit NLTK library for our NLP tasks. And then we are importing snowball stemmer and Lowen stemmer for stemming functionality. And we are then giving a sample input words for on which the stemming has to be performed. And these are the sample input words. And then we are defining the stemmers, that is your snowball stemmer and Lowen stemmer. And these two are taking the words as an input. The words are nothing but which we have predefined here. Clear? And then after defining these stemming functions, each function will call the list of words, and these will finally print you the stemmed words. Okay, that is the chopped off words. So then let us look at the output, how it will look like. So for the snowball stemmer, the output is this: run, runner, ran, easily, happy, happy, play, play. For Lowen stemmer output, the output looks like run, runner, ran, easily, happy, happy, play, play. So you can see the stemming process, how it have been working out. So it is just trying to remove your affixes and the other things and trying to bring it to the base word. So, but if you can see, there is a word called easily, EASILI, EASILI. So then you should have a question here. So the word is EASILY, right? So what happened here is, so generally the stemming will try to remove the suffixes, suffix or prefix or infix, right? So when it found this word called easily, EASILY, the suffix ly is a common adverbial ending, as you know. So it just stemmed it, or it just removed this suffix, which now resulted into EASILY. So where the remaining portion, that is EASI, when it have removed the ly, doesn't form a valid English word, but it represents some truncated form of the original word. So the root forms what it have done right now is, so it just stemmed to EASILI. Okay, so which will indicate the word called is. Okay, which indicates your connection to the word called root word called is, where, but this is not a proper dictionary word. So this is how in our earlier slide we discussed, it doesn't guarantee us a valid word as an output, whereas lemmatization will guarantee us the valid word as an output. So hope you understood, students. Thank you.